Okay, so hi everyone. I'm very happy to be here to present my work today. So let's go to it. Okay, so as it has just been said, I'm from the Quantum Neurobiology Lab led by Professor Dr. Craddock, who just presented. So we are in Canada, so I should first update this. It's not always snowing in Canada. Sometimes we have nice weather, so right now it's very sunny. So what we do in our lab, we are looking at quantum biology effects, and we focus on the brain. So we look at light interaction in the brain, also magnetic field, you will just have heard about it, and also chemical. We have nice poster also about it. And so what we do, we have this brain. So now I'm speaking to you. You are trying to understand me with my nice French accent with your brain. And me are trying to make me understandable. And so we are all using this brain. So it's very, I think, important to understand it. When you look at a quantum perspective, you have different candidates. Like there is, I think, like a lot of different candidates we could look at. But what I do in my projects is I focus on microtubules. So they have a very interesting candidate because first they are in the neurons that is in our brain. And inside this neuron, what we have is different elements. So for example, microfilament, microtubule, or intermediate filament. So I focus on the microtubule part. The microtubule is made up this dimer, alpha and beta tubulin, as you can see on the screen. But for this work, we need to go to not just stop at the tubulin. So we go also to the residue part. So inside, for example, you have tryptophan, tyrosine, or phenylalanine, and other residues. But these are the three important for this work. So now what we do, we put our quantum glasses. What I mean by this is we use like quantum mechanics to study this system. So it's not about, for me, microtubule and all to be in classical or quantum. Is my decision to use this tool of quantum mechanics to study it, to get maybe a better understanding of this reality of the microtubule. So how do we do this? First, we bring down a bit the system. So now it's not the big microtubule, it's a network of tryptophan. And there is 8 tryptophan in the tubulin. So one tryptophan is, you can see it's a very complicated molecule, not that much, but a bit. But we reduce it to a 2-level system. So you have the ground state and the excited states. So now it's just a 2-level system. And how strongly it interacts with the light is what will define our tryptophan. And it's what we call the transition dipole moment. So higher it is, like it gives also the direction of this interaction with the electromagnetic field, but also the strength. There is a lot you may imagine for every molecules, but the two most important one for us is 1LA and 1LB. And in this talk, like all the tryptophan are in the 1LA transition. So now let's say all the tryptophan are just an arrow and a position in this model. So now let's talk a little bit about superradiance. So what is superradiance is not about the transport here, but is about a collective emission of light. So if you start with one excitation, this can be shared across this network of tryptophans. And if they are in phase, this coherence is in phase, is what we call superradiant state. But if they are out of phase, is what we will call subradiant state. So how does this work? So first, you excite your network of tryptophan because they all share this current coupling inside your network. When you excite here, actually, what happens is a delocalization of this excitation. So now it's shared across the network. this network can be decomposed in some exciton, and if okay, someone is calling. So now let's go to some the mathematical framework behind this. So it has been studied before, for example, by Dr. Korean, who is just here, but we use the same Hamiltonian, the non-Hermitian Hamiltonian here. In this framework, so you first have the on-site excitation energy. So each tryptophan energy is a 280 nanometer. And then you have the current coupling, so how the interaction between this tryptophan. And you have also the dissipative coupling, which is here the radiative decay of this full network of tryptophan together, how they radiate the electromagnetic field to the environment. So when you have, remember, so we had all this network with a different position and all. So with this Hamiltonian, you can diagonalize it and get the eigenvalues and eigenvector of your system. But because it's a non-Hermitian Hamiltonian, you have the real part and the imaginary part. The real part will give you the energy of each exciton, and the imaginary part, the decay rate for each exciton in our system. So how we do this? We first go to the protein database, and you can get the tubulin. So, but inside there is a lot of different elements. So you just take the tryptophan from it, and then you construct your microtubule with this dimer of tubulin. And from it, you extract the tryptophan data. So what do you extract? You extract the position and the transition dipole moment for each of these tryptophan. What we look at in this study, and it has also been done before, we look at the quantum yield. So the quantum yield here is the formula. You have the radiative decay rate that we saw in the Hamiltonian, and the non-radiative decay part is, if you want, what's the light that we cannot see from our system, that is lost in our system. And we take the thermal average, so you just actually you average over all the exciton of your system, and like this you have a nice formula that you will see we can compare between experimental studies. So what to keep in mind for those who don't like too much maths? For example, the quantum yield is just emitted over the absorbent photons. So higher is the quantum yield, more efficient will be the light emission. And superradiant state is this collective synchronized emission in our system. So let's go to results. So in the results, what we do, we start with a molecular dynamic simulation of this tubulin. And then for the quantum yield, before what has been done is we take the same protein, like from the protein database, you take the same protein and you just repeat it to create the microtubule. So as you may think, there is kind of a symmetry in our system. So to break a bit this symmetry, we took the molecular dynamic simulation and extract snapshot of the tubulin to construct a more disordered microtubule. And you can see when you increase the size of the microtubule from one filament, which is 13 dimer of tubulin, you can see this increase in quantum yield. Same with random snapshot and with the same PDB. Then what we do, we try to engineer this quantum yield. First, here is a reference from before. We remove one tryptophan, and what we see is that there is an increase in quantum yield. Tryptophan 3 here is interesting because there is some parasite actually that are tubulin without this tryptophan 3 that could be maybe used, but hard in experiments. So what we do is we take also a tryptophan from outside that will bound to the tubulin. So now our network will not be 8 tryptophan, but 9 tryptophan. And we look at different different ratio of this tryptophan bound to this tubulin. So when I say 25%, it means that in my microtubule, say 25% of the tubulin, which has a tryptophan that is bound to it, and 75%, which is normal tubulin without bounded tryptophan. So 100% is just bounded tryptophan to tubulin. And you can see this very high decrease in the quantum yield in theory, in our theoretical framework. So what we do some experiment with this. We take this tubulin and microtubule solution, and we do some spectrophotometry with it. We look at the absorbance and the fluorescence spectra of our solution. And we look at the quantum yield, which is approximatively like the fluorescence over the absorbance to make it simple. And we add tryptophan in different ratio in order to test if this quantum yield will change. So if tryptophan will have an effect on the optical responses of microtubule and tubulin. So what we see, we measure it at 280 and 295. So we excite our system, and we calculate the change in quantum yield in between the microtubule without tryptophan and with added tryptophan. And we compare it with the theory that we had before. So here in the result, what you can see is like 0.25 is a 25%, could like be mapped to for the theoretical part, and 1 is the same ratio, if you want, is the same quantity of tubulin and tryptophan in the solution. And we can see, like in theory, remember we had this sharp decrease, and here we saw the same decrease at 280, 295, so the same trend in the quantum yield. So this was interesting results that added tryptophan can quench this microtubule fluorescence. And it was a similar trend than theory, so we want to move this forward and maybe add other elements than tryptophan. Here it was easier to add tryptophan because our network, our starting network was already tryptophan, so but we could go forward with this. And as a conclusion, so there is a lot, it's not as easy as it is, as you may think, but there is a lot of, for example, experimental challenge. For example, microtubule have a high background scatterings that we need to deal with. And so we need also more experiment to clearly distinguish between quantum and classical effect in microtubules. Also in the theoretical side, we need the environment to be more realistic, maybe add the non-Markovian part, and also to not stop at point dipole, especially if we add other residue, which should be at shorter distance from each other. And so the next step, like as you can see here, would be to, for example, complexify the network to make it not just tryptophan, but add tyrosine, or also GTP or GDP. So the main reference for this work is on arXiv if you want to check it for all the details. I needed to cut it short. And also, it's very aligned with this conference. We have a preprint on quantum in biology, quantum for biology, and biology for quantum. So if you have any feedback, because it's for the whole community, it would be nice to hear. And just a bit of advertising for the people of my group. Go see their poster. They are very nice. So, Köszönöm, thank you. If you have